if the last session was a little bit dry, going into data types and why we should be, why we should use them and some of the problems that we might encounter with them, it was very, very important. And they're the sort of basics that you need to nail to then go on to be a very good programmer in the future. But now we're going to do something a little bit more, well, I think a little bit more interesting. And it's going to be a little bit quick and dirty. We're going to try and do it to time this time. But we're going to try and predict the boiling points of some hydrocarbons. You know, I'm a chemist. Sammy and Nikki, well, Nikki was originally a chemist. Sammy now works in a chemistry department. So this is something where we can use machine learning, very, very simple machine learning, but still machine learning, and data that we get experimentally to do some predictions and maybe save ourselves some time and money in the future in the labs. So let's kick off and let's try and do this a little bit properly. So the first thing we want to do is we just want to put a bit of markdown at the top. We want to name our Jupyter notebook. We want to title it something useful. So prediction, actually we can do one better. Prediction of hydrocarbon boiling points. See if I got this right. There we go. Oh, no, I haven't. There we go. So we've used some markdown to name our file. And the first thing that we always want to do is we want to import the libraries that we'll need. So import NumPy as NP, import pandas as PD, and import matplotlib.pyplot as plot. And now I know that I'm going to need these libraries because I've obviously done this, this before. But if you were doing this in real life, you might not actually know exactly what libraries you will need. So you will have to obviously come back and update them as and when. So that should all work for you guys if you manage to install them into your Conda environment as we put up on the screen at the beginning. And now you just need to import them into Jupyter so that we can go and use them. And all we've done here is we've imported NumPy, and because we don't want to write NUMPY every single time we want to call a function from it, we've shortened it to MP. And we've done the same with pandas here. We've shortened it to PD and matplotlib PLT. And this is just a lazy thing. You can shorten these to whatever you like, but these are the standardized ones that people use. And NumPy is numerical Python. Pandas is a library for bringing in and using data nicely and easily. And matplotlib.pyplot, which is a bit of a mouthful, is for graphing results. So now we want to import the data set. So let's say importing the data set. And here I'm going to show you a little trick that I always use. And I'm doing this on a Mac, so my file tree might look a little different to yours. And I'm going to put the one that works for me first, and then I'll attempt to show you how to do it differently on a Windows machine afterwards. So I always define what I call a root, and my file is in users, sam2u17, and my desktop. And then the actual file that I want, so my hydrocarbon data frame is read CSV, is called hc long list.csv, and we want to go to format root. Okay, so I've now loaded that in. For those of you using Windows, you might need to do something like the following, where you say root equals R, then your speech marks, and then you will need to put in the path to wherever you saved your folder. And so if your folder was in users Sam desktop, you would still have to do something slightly different, because you would have users and then a backslash, and then Sam, then a backslash, then onto your desktop. But your file may be saved somewhere slightly differently, slightly different to mine. So don't just put in users SAM desktop. That's just the path that we are following to find our file. And the setup I've done here is that most things are saved on my desktop. So when I want to read things in, I don't always want to have to write in this whole file tree. I want to be able to define it as a variable name, so root, and then I just want to get the individual files that I want from, in this case, my desktop. And so by doing this, we are putting root, or this string, in place of these curly brackets automatically. And therefore, I've been able to read in my hydrocarbon data frame, and I've done it using the pandas read CSV function. So if we're going to be really on top of things here, we need to say file path, and we need to put a comment here saying hydrocarbon data frame. Excellent. So now I suppose what we'd like to do is have a look at what we have loaded in. So we can simply call our hydrocarbons data frame, and we run it, and we have nicely now loaded in that CSV file. And it's quite long. We can see that it's got names, the IUPAC names. This is for people that are not in chemistry, though I assume a lot of you are. This is the international identifiers. So this is what everyone has agreed that we should call these chemicals. And we've got number of carbons here. We've got the melting points and the boiling points. And we might not actually want to look at the whole data frame. It may be that we just want to look at a little bit of it to check that it looks like we expect it to look. So we say, hey, hydrocarbon data frame, and we put the dot head, and it just returns the first 5. Or we could, in fact, do the last 5. So we say hydrocarbon dot data frame, and we look at the tail. So here we have the first 5 in there and the last 5. That's just a way of breaking it up if you don't want to look at the whole data frame at once. Now, the first thing we should really do is get a few values back that tell us a little bit more about what's going on in this data. And remember, what we're looking to do here, as we put at the top, is we're trying to predict the boiling points of hydrocarbons. So this is, a little bit, it's a little bit mathsy, and so it might be good if we, bring back the count, so the number of data points we have of each, the mean of each, the standard deviations, the mins, the maxes, and a few ranges. And actually, at the moment, this probably doesn't tell us too much information, but it's always good to have a little look, especially if you have an idea of what you should be seeing in your data set. So if you know the mean should be around 80, you can do this, and the mean should be around 5.5 for the melting points. You can do this and you can see that, okay, yes, I've not done anything ridiculous when I've imported this data. I've not broken it. It's exactly how I expect. So we might want to then next look into plotting some of the information to see what the trends look like. And as a chemist, I know that the boiling point of hydrocarbons is in a way related to the number of carbon atoms they have. So it might be quite good for us to define X as the number of carbons, and we do this like this. And it might be good to define Y as the thing that we would like to predict. And we do that in this fashion. So here, all we've said is we've defined the variable name of X and Y, because we like plotting things against X and Y. We've said we want to look in our data frame that we've made, and we want to pull out the column that's titled NC and the column that's entitled BP. No error messages, nothing's really happened. So now what we would like to do is plot this. And we can do this quite quick and dirty. We could just say a scatter plot, plot.scatter xy. And here we've called from the matplotlib library, we've called the function that allows us to plot a scatter plot of two variables. And here we've put in our variable names, which again are pointers to something or containers for something. And excellent, we see that there's actually quite a nice trend, but this isn't a very good graph, really. If we're thinking back to when I gave the talk and we're thinking, well, is our code understandable? Is it readable? Are we going to know what's going on when we come back to it later? Is somebody else going to understand what's going on here? Probably not. So actually, let's do some proper plotting. And the way we do that is we set up a figure and we set up some axes, and we define our figure and our axes, and we say plot. And the thing that you need to write for that, the thing that you need to call is this. Again, we're using the matplotlib library. We're using the subplot function, and we want to add to our axes. So we want to add to our axes a scatter plot of x and y. And actually what we want to do as well is we want to label our axes. So we say x.label, and this is what the number of carbon atoms. And if we go ax.set y label, and we say the boiling point, and this is in Kelvin, I believe. So we can see here that we've taken in two variable names, which are pointers to some data. We've asked it to plot them as a scatter graph. And here we've inputted two strings into our onto our axes, because we want to set our x-axis to have a name of this and our y-axis to have a name like this. So if we plot this, we can see that actually now our graph is looking much better. People are going to understand what's going on here. And in actual fact, what I haven't done is I haven't commented this code. And I haven't commented this code. And going through this, I'm going to break one of my cardinal rules that I've told you to do, which is you should always be commenting. You should always be making it explicit. But in the interests of time here, I'm just going to describe it to you. But when you are doing it, I know I'm not practicing what I'm preaching, but you should definitely be commenting this and making it proper. So we can still do something a little bit more to this. We can add a title. And that's probably very useful if you need to show this. You need to print this out and you need to show it to people in real life. And again, that's very easy. Following the same format, we're going to add a title to our axes. And this title will be boiling points of linear hydrocarbons. Here we go. Now we've added even more to our graph. We have a title and we have some axes. Now I was going to show you how we can add names to each of these points, but actually on my screen, the points are so close together that the names are all overlapped, and it's a little bit outside the scope of what I want to show you today to start delving into the depths of the matplotlib library to make the graphs appear differently. So if you would like to know how to do that, feel free to ping me an email or put it in the chat, and I will get back to you and show you some more fine tuning you can do of these graphs. Great, so we have a trend there that we're looking at. We can see that the boiling point sort of follows a nice curve upwards and round, all to do with the number of carbon atoms. So I think we should probably just jump straight into doing some nice predictions. Let's begin by doing a very simple linear regression with one independent variable and one dependent variable. That might seem a little bit silly to some of you that have done these things before, because it doesn't really look like a simple linear regression will fit this very well. But it's an important lesson to learn that we should always start with the most simplest method of doing things. And even in some of the work that I do, where I'm implementing big machine learning systems, big machine learning pipelines for for companies so that they can predict the values of their outputs without having to spend money doing it in the lab, I still always start with a simple linear regression when I'm tackling a new problem for them, or a simple classification. And there's the reason for that is that you need a baseline to work from. And also part of the Zen of Python is simpler is better than complicated. So if your simple linear regression works well, there's no point implementing, excuse me, a very complicated set of algorithms for not much more gain. So the first thing I'll do is I'm going to make a new data frame because I only want to bring out the boiling point and the number of carbon atoms. So I will name this my new linear regression hydrocarbon data frame. And if you see, I'm using underscores. I'm not having any white space here because we know that doesn't work. And it's actually very easy to pull out some columns from your original data frame. You can say, now I want to use my original data frame, and I want to pull out the number of carbons and the boiling point. Oh, excuse me, and they have to be strings. And what I'm going to do here is I'm just going to put this dot copy. And what this means I'm not now going to inadvertently alter my original data set. Because if we inadvertently alter our original data set, we're then not using the proper data at all. So if I make a copy of it and I put it into this new one, I can be assured that nothing is going to go a bit skew-whiff later on. So we've made our new data set. We can copy and we can paste this into here. Our new data frame. And we've now got a data frame that only contains the number of carbons and the boiling point. And I'll just quickly scroll up just to show you the difference in the two data frames. So we've pulled out this column here, the number of carbons, and this column here, the boiling point. Great. We want to do some prediction. And the first thing that we might want to do then is to split the data into attributes and labels. So attributes are the independent variables, whilst the labels are the dependent variables that we want to predict. So we want to predict their value. And excuse me, we can do that quite simply. And we do it by just using some of the inbuilt functionality of pandas. So let's say our X for our linear regression is, what did we call this? We called this our new linear regression hydrocarbon data frame. We're going to use the iloc function. And we're going to use, oops, why is it not typing? We're going to be using some slicing and indexing. And this looks a little bit more complex than what I showed you in the last session, but it's actually not really. It's essentially what we're saying here is we're not defining a first value, so we want everything after that and up until this point here. And we're just reshaping it to be a 2D array instead of a one-dimensional array. And that's because what we need to do later on needs a two-dimensional array. And that might sound, what have we done wrong here? It's not value, it's values. And that might sound a bit abstract, so let me show you what I mean. So if we look at our new array, we can see that every single number, so this is our number of carbons, we have an input, and then we have a comma and nothing. And then we have input, comma, like this. And if we look instead at our original, which we had called X, you can see that this is just a series and it's one-dimensional. So we've changed from a one-dimensional set of numbers to a two-dimensional array. And don't don't get too hung up on why we've had to do that. It's just we have to do that to appease some of the libraries that we're going to be using later. Again, if you want a bit more of a more in-depth and less fluffy explanation to that, ping me a message and I'll be happy to talk to you a little bit more about that at length. But in the interest of time and the level that we're working at here, I'm just going to give it to you and you're just going to have to take it on face value. Okay, so we've made our new X1 and we now want to make our Y. So we can copy and paste most of this there like that. But this time, instead of taking the first index, the 0th index, so the first one, we're going to take the second column. So here we've taken the first column, and here we just want everything from the second column. So this is saying I want everything from our second column, but as we know, it's the first index. Got values, and then we need to reshape it to be a two-dimensional array again. Excuse me. And here we go. We now have our new X data and our new Y data, our new independent variables in a format that is going to allow us to use them. And this is something that you will find when you go and do your own Python projects. You're always going to have to spend a lot of time finding the right format for your data to then go and use it in the programs or the libraries that you need to use it in. So this is half the battle right here. So now we've got our dependent variables and our independent variables split out. We want to split them into a training set and a testing set. So we want to be able to have a reduced set of our data to train our prediction algorithm on. We don't want it to have seen our test set of data because we want to apply our prediction algorithm to that test set blind so that we know how good it will be at predicting new information when it comes in. And this is actually quite easy to do. We need something called, we need the function called the train test split. But that function comes from the scikit-learn library. And I didn't actually import that at the top. So what we need to do is we need to go back to the top of our Jupyter notebooks, and we need to say from the sklearn library, and in fact, we want the section of it that is the linear model. We want to import, no, sorry, not the linear model section, the model selection section. Model selection. We want to import the train test split functionality. And we need to rerun this code cell, this code chunk, so that that's imported so that we can use this functionality. What this will do, this will automatically split up our data into a training and testing sections. So if we come back down to where we are working, we can now say, or we can now ask it, sorry, to split our data up. And what we want is we want our X training data and we want our X testing data. So we want the two to be separate. We want our Y training data and our Y test data. So that's 4 new variables we have defined here, 4 new containers for 4 different types of information. And we very simply call the train test split. And into it, we're going to put our data here that we've already defined, our X linear regression data, our Y linear regression data. And we can now define a few different things. So we can tweak how this train test split works. So what we actually want to say is we want to say our test size of 20% or 0.2. So it's going to split it. So it trains the algorithm on 80% of the data, and then it tests the predictive power on 20% of the data. And then I'm just going to set our random state to 0. Again, we're just defining how it chooses this information, how it chooses the information from the original data set. So if we now run this, again, no error messages, that's great. So everything seems to be working smoothly. So this is really good. We now want to define and set the algorithms that we want to use. So now, again, we need to go back to the top of our Jupyter notebook, because now what we need to do is we need to import some more functionality from the sklearn library. So here we want to say from sklearn, and from it the section, the linear model section, because we want to use a linear model, a linear regression. Lo and behold, we want to import the linear regression part of it. And again, we have to rerun this code cell. Every time you import something new, we need to rerun what's going on. We need to rerun the chunk so that we have actually imported what it is we want to have imported. Okay, so now back down to where we are working. And here we now need to define an instance. It's what's called defining an instance of our algorithm. So let's call it our regressor, because that's what it's going to do. It's going to perform a linear regression for us. And here we simply call the linear regression function. And you can see that we've not put anything in it just yet. So here, we've basically, what we've done here, without getting too technical, is we've basically loaded it. We've loaded the chamber, and now what we need to do is we need to shoot it. So we say regressor dot fit x train y train. So we've chambered it. We've said, right, we're going to get an instance of you here. And now what we need to do is we need to apply you to our data. And I've missed underscore there. And we want to apply it to our training data. Now, remember, this is the 80% that we split out from the original 100% of the data, because we're going to use that to train the algorithm so that it gets good, or hopefully it gets good at predicting. So if we run this now, brilliant. We get this output that basically says it's worked, essentially, which is good. Now what we can do is we can have a look at how well it's worked. So if we call the print function, we want to find the regressor's intercept. We can do that. What have I done wrong here? That should be a dot, sorry. There we go. We can see we have an intercept of 62.2. Okay, does that really mean anything to us at the moment? Not sure. So then let's have a little look at the coefficient of x. So we can have our regressor, sorry, I've done it again. It should be a dot, regressor coefficient. Okay, coefficient of 10. So that means we're breaking the axis at the value of 10. I don't know if this sounds like it's going to be very good. So now then, let's go ahead and make some predictions and see whether or not this is any good. So now what we want to do is we want to take, we want to define something new called y predictions. So we are now, this is what we actually want to predict. We need a container for the values that we're now going to predict. And we simply say regressor dot predict from our test sets of x values. So just to break this down, we want to say from our 80% of boiling points, from our 80% of our number of carbons that we've broken out, we want to predict upon that, and we want to put that into this variable here, this container called yPredict, and this will contain all the values that it has gone on and predicted. And we can see now that that was very quick. Some models that you run that are more complex will take an awful lot longer to run. Now, these values that we printed out here, unless you really know the data well, they're not really telling us too much. So a better way of showing how well we've done would be to plot it. So now we can do quite just a quick and dirty plot again here, where we plot our X test against our Y test as a scatter. Okay, so these are the values that were in our test set. So this is the 20%. And these are the real values. These are the values from the data. What we can do now is we can say, okay, let's see how our predicted values stack up against them. And let's plot that as a line. And we want to, so that it's really obvious, we want to set the color of the line to red. Let's plot that. Oh, what have I done here? This might be why, because, oh, no, it's because they use American and we have to have color instead of color. Okay, well, that's not a brilliant fit, really, is it? We can see that our error here is quite significant. And remember, we've not done anything fancy here to look into this. We've simply said here that we just want to plot some of our predicted values against some of our actual points from the data set. And yeah, it seems to do quite well at the bottom here, but I wouldn't be too sure about that. But as we come up through the number of carbons, it gets quite bad. So let's plot this properly, because this is actually quite an interesting, it's quite an interesting graph to show how poorly this is. And I'm going to be lazy here and show you something that I do all the time. And what I'm going to do is I'm going to scroll back up and I'm going to copy and paste code that I've used before. And this is something that everyone does, so don't feel too bad about it. So I know this code works, and I know it basically sets up what I need it to do. So I'm going to copy that. I'm going to bring it down here. And now we need to set a new figure, so figure 1 and ax1, because we don't want to reuse variable names. And so on our ax1, we want to plot a scatter graph of x test and y test. And on axis 1, we want to set our X label again. So it's just the number of carbon atoms. That's exactly the same. And again, we want to set the Y label to the boiling point, because again, that's the same. However, we need to update the title name. So the title now should be predictions of boiling points using linear regression. Excellent. So, oh, and I haven't, this is one of the issues with copying and pasting. I haven't updated this to be our new axes. Fantastic. And I need to add in, our plot of the predictions, the predicted values, sorry. So let's go x.plot, and we know that it is x test, y predicted, and color. Again, we want to set it to red. Set this to what you like, just to make it pop out from the page. There we go. And nothing's interesting. Nothing has happened. So let's just try. There we go. So boiling points up the side, number of carbon atoms, predictions of boiling points using a linear regression. As a takeaway, you might want to dig a bit deeper into this and find out what some of the errors are here. It's quite simple to find the error that this model is returning. And you might want to extrapolate this to the whole data set. Or we might want to try changing our test train split to see if we can increase the predictive power of the model. So to do that, what we might want to do is scroll back up and very simply change the test size to 10%. So if we do that, we then have to rerun all of these code chunks. And I did that quite quickly. So what I've done is I've scrolled back up to where we do the test train split, and I've changed our testing size to just 10% of the data. And we need to rerun all of these code chunks here. And we can see that, this isn't too good, is it? So we run the risk here of overfitting our data. If we train on too high a number of data points and test on too low a number, we're essentially giving the algorithm the answer without allowing it to come to the answer itself. And that's pretty bad, because then when we need to try and extrapolate it onto new data, it will perform poorly. We can also see a problem here in that we're predicting on a very few number of data points. So again, this isn't great when we're trying to do prediction here. This is basically, we can't be very confident of the predictive power of this model, even though we see that the trend is following a similar trend to the real values. This isn't a great model. We could sit here and we could play with it all day, try and tweak it, but it might be, from this initial look, might not be the right model for us. So what can we do? Well, maybe we should look into using multilinear regression instead. So to do a multilinear regression, we will take two variables that we will use to predict, I should say. So we will still be trying to predict the boiling point, but now if we scroll up and have a look at our data set, we can see that we have the melting points too here. So maybe we'll get a better fit if we take in the number of carbons and the melting points. Maybe then, if we plug them into a multilinear regression, we might be able to predict the values of the boiling points a little bit better. So let's go ahead and try it. And you'll see that actually the setup is incredibly similar. The format is always very similar. So now I'm going to go into Markdown mode, and I'm going to call this, it's a new section. So we're going to have it in bold, and we're going to underline it. And we're going to say multilinear regression. Oh, I keep doing that. Way, there we go. Multilinear regression test. And again, we're going to set this up in exactly the same way. But what we might want to do this time is define some new data frames. So just like before, we might want to define our new X data frame for our multilinear regression. So our X multilinear regression data frame, we will take our hydrocarbon data frame, and because I've got a terrible memory, I can't remember what I called it. So here it is, it's HCDF. And from that, we want to take 2 columns this time instead of 1 column. And if you remember before, we just took the number of carbons, but this time we want to take the melting points as well. And there we go. So we've got the number of carbons in here and the melting points because we want to see if this is going to improve our prediction accuracy. And as before, our Y is still going to be our boiling points because this is what we are trying to predict. So if we put our boiling points in there, and you'll see that even though we're doing something quite different, the setup and the format is exactly the same. So let's do that. And just for our own sanity, let's check that it's worked. Data frame. Aha, brilliant. And we don't want to look at everything, so let's just look at the head, the first 5, and we can say that that we've got the number of carbons in here and we've got the melting points. Fantastic. So it's worked. What we would like to do now is look into using, again, a regressor. So let's call this our multilinear regression regressor, exactly as we did before. And this is going to equal our linear model dot linear regression. Okay, fantastic. And then what we want to do is run that. Okay, what have I done wrong here? Regressor. It's telling us that linear model is not defined. So where have we gone wrong here? Aha, yes, what I haven't done is I haven't imported linear model from sklearn. There we go. So what we need to do is we need to go back to the top here and we need to say from sklearn import linear model. Fantastic. And remember to run that cell again so that we can use the functionality here. And what I'd done before is I'd imported a specific part of the linear model library. I just imported the linear regression. What we've done now is we've imported the whole part. And I had completely forgotten, but what I wanted to do here was show you that something called namespaces, and that namespaces matter. So whereas before we simply typed in linear regression and used it, what I've done now is I've had to call linear model dot linear regression, or have called linear model dot linear regression, and this is something called a namespace. So if we had just used the linear regression part of the function, that would have been fine. But here we're calling from linear model. And this is because up at the top, where we were importing our different libraries, we had set the namespaces differently. So as you see, I got myself, I ran into a little bit of a problem here because the name linear model had not been defined, even though I knew that I had this linear regression functionality already here. And so this is something that you need to be aware of, that namespaces matter and the way that you import things matter. Okay, fantastic. So now that it's worked, we can now use it to do our fit. And we say multi-regression regressor, and we want to fit it to X multi-regression data frame. And we also want it to go to our Y data frame. Fantastic. And we'll see here that this is now markedly different to what we did before, because we're still predicting the boiling points, but this time, instead of just putting in one predictor, we're putting in both. So let's run that. And we can see that it's worked. Again, this is just basically telling us that everything's okay. And we can, in a different way this time, we can print out the intercept. So let's put our regressor dot intercept. And we can also print out, oh, excuse me, we need that. We can also print out our coefficients. And this is our MR regressor coefficients. And again, this is a dot, it is not a underscore. Fantastic. So here, in a slightly different fashion to how I did it before, I've asked it to print the string intercept, and then I've told it to make a new line. And so it's printed out intercept, and then it's printed out the value of our intercept from our regressor. And here you will see that we're using different data types because, you know, we're putting a string in here, and these are numbers. And we're putting them into the print function in a way that makes it easy to read. I could indeed get rid of these new line commands and run it again, and you'll see that it prints it out very nicely to screen. Our intercept is 208, and our coefficients, or our weights for the model, are these values here. Again, they don't really look like anything that tells us whether or not the model has worked well. So now what I'm going to do is I'm going to introduce you to something called stats models. And this will enable you to print out, if anyone's used R, to print out a really nice regressions results table. So again, we need to go back to the top of our Jupyter notebook, sorry. And we need to now import the stats model API as SM. So all we're doing here is it's a new library, and we want to import some of its functionality into our script. And again, we got to rerun that. What have I done wrong here? It's stats models, not stats model. And so we've run that. So now we go back down to the bottom of our Jupyter notebook to where we are working. And one of the things that we want to do first with stats models is we just want to add in the constants, because obviously that's going to be quite important for bringing out all the results. So we want to put in data frame. What have we done wrong here? Oh, excuse me. No, I've done that completely wrong because we need to do sm dot add constant. There we go. So we've called again from the stats models library, and we need these constants so that we can print out some of the results of our regression. Now we need to run the model, and you'll see now that this is a slightly different way of running a regression model, but again, it's just as valid. But doing it this way, we get a better output, and hopefully we get a better prediction. And so we need to then fit again. We need to fit our ordinary least squares model, and let's run that. Okay. No, it's because I had called it for the data frame, hadn't I? So. And just whilst I've got this error message on screen, for those of you that are not as familiar with Python, the error messages in Python are great. It's told us that there's a name error, and it literally tells us that the name YMR that I'd written in first isn't defined. So that tells me straight away that there's a problem in this exact part of the code so that I can go and troubleshoot it. And that's one of the things that Python is great at. Other programming languages, they don't really tell you what the problem is. Some do, others don't. Those of you that have experience in Fortran, you'll know that Fortran's an absolute nightmare when you're trying to debug. So let's fit that model. Let's do some predictions. So let's call our predictions. and we will say to do the predictions on our model, obviously. So let's predict our XMR data frame and run that. Great, nothing wrong there. So let's print our model. And this will be, let's print the summary of our model. And this is why stats is, the stats API is so good. If we run this, what have we done wrong here? Print model.summary. One of the joys of doing a live code along is when it all goes wrong, you have to try and figure out what's gone wrong. Here we go. That's what I've done wrong. It should be model.summary instead of underscore, model_summary. Fantastic. So, and then if we print that out to the screen, and what had happened there, if I just go back a second, I'd gone model_summary when actually what I wanted to do was use what's called the dot operator, and which is this. And the dot operator then allows us to call the summary functionality from model. Whereas what I was doing was I was doing something stupid and wrong. So by using the underscore, and by using the underscore in that fashion, you won't be able to pull out this functionality. And so if we then print that, we can see that we get this lovely table. It tells us that we've got a great R squared, got a great adjusted R squared. So everything seems to be pretty good. We can see some of our constants, our T values, our kurtosis down here. So it seems to be pretty good, but there might be a few issues looking at some of these more involved descriptors down here. And in this case, I haven't made a test train split. Nikki's just told me that we haven't, reminded me that we haven't done that. And that's fine, actually, in this regard. We did it first because that's probably the proper way and the better way of doing it. But when you are using the stats models API here, and you're making a multilinear regression in this fashion, it does a lot of the stuff under the hood. So it's not the end of the world that we haven't done that. So yeah, this looks like it could be quite a good model and something to go forward with quite well. But again, these are just numbers. We're not very good at interpreting numbers that well. So the best thing that we can do is to graph them. And so if we very quickly and dirtily plot a scatter of our original values, what did I call them? There we go. So these are our original values for our hydrocarbons, for our boiling points as the number of carbons increases. And then if we plot over that, and I might introduce you to a new function here. If we plot over that our predicted values, and I'll just come back. I'll do this very quickly and then I'll come back and describe it. We can see that actually we have pretty good accuracy up until we get to about the 35 carbon, the chain length of 35 carbons. So again, we've just done that very quickly and dirtily, which is something that Jupyter notebooks are great for, and it's something as scientists we just want to use it as a tool that will either confirm or shoot down what we hope is happening. So let's just go and make this as a final point. Let's just make this graph a little bit nicer so that we can so that we're completely sure what's going on. And again, like I did before, I'm simply going to steal some code I've written before. And as you get more and more used to programming, you'll know that most of your life is just spent either reusing or stealing code. And that's something that you shouldn't be too worried about. What do we have here? And then what we want to do is we simply want this to be that. And with any luck, this might, oh, no. No, that's not what we want. We want that to just be our originals. And there we go. And this wants to be a multilinear regression. Fantastic. So now we can see actually up until about the 35 carbon atoms, we've got quite a good fit. And then for some reason, it goes off horribly towards the end. So I think I'm coming pretty much to the end of the session here. What we've done is we've read in some data. It was quite a nice data set. There was it all seemed to be, there were no missing values. They all seemed to be using the same units. And so this was a very, very nice data set to use. It was very well formatted. So we read it in, we looked into it a little bit, very, very quickly, just by graphing it and looking at some of the descripting points like standard deviations or the means. We made a linear regression model using a single variable, using the sklearn library, and it didn't work very well. And then we went one step further, and we decided to print out some more in-depth statistics and use a little bit more complex model to the data. And then we plotted it again, and we see that we've got a slightly better model, but it still breaks down. So going forward from here, you might want to look into some more complex models, but actually that's not always the first step you should take. You might want to look into changing the data slightly in some way, so that you, for instance, you might want to log it, or you might want to look into if there's some more less linear relationships. So there's a lot of tweaking that can be done here, even on these very simple models. And I think that's probably a good place to end. And I'll just have a look at the chat. It looked like Nikki was on top of most things again. So there's a question here from David, said, if you wanted to fit the boiling point curve to a log or square root function, how would you do that? Okay, great question. And it actually brings me back, if we scroll back up to when we create our new data frames. So here we have we've made our new data frames, and what we've done is we brought in the number of carbons column and the melting point column, and you can very simply take the values from these, and you can use NumPy, numerical Python, and it will be np.square root of the values in that column and plug that straight back into your model. So it's actually really, really simple. Or if you wanted to take the log, again, you can use NumPy, numerical Python, and you go np.log of the values from the data set and plug them straight into your model. So at this point here, you can play about with your data and make it however you want to make it. And then we've got another question that says, why did you reshape the data set to make it two-dimensional for the first one, but not the second? And again, this is something that you will come across quite a lot, in that you have to get your data to fit the libraries that you're using. So when we did the first prediction, we used the sklearn library. And in the second prediction, we were using the stats models library. And even though we're doing nominally the same thing, we're still doing a regression. They require different inputs. And the inputs are, in a sense, exactly the same, because you're just inputting the values from your data, but they require them in different ways. So it's actually a really good question, and something that I hope I demonstrated in this talk, that it's not always going to be exactly the same. Making the model is the easy part. You know, we made our model and made our predictions here in 4 or 5 lines of code, but it's factoring and reformatting the information so that it can go into the model that's going to take the most of your time, and is where the problem's going to come. And so the only reason I didn't do it was because I didn't need to for the stats model way of doing things, but you have to for the sklearn way of doing things. And I think then if there's no more questions, we've come quite nicely to time.